we know what the solution of a system of equations, or rather just one equation is. The solution to an equation is a set of all points. Make a true statement when you plug it in for a variable or variables. We know that to be true. But graphically speaking, all those points fall on the line or fall on the curve. So when we talk about a linear equation, one of the things we can do is we can make a table of values. If we're trying to graph it out, we can make a table of values of x and the corresponding y value that we get. Okay, and then we'll know that that xy ordered pair is on the curve or on the line. I'll show you what I'm talking about here with example 4. We've got this equation, y equals negative 1/3 x plus 2. Okay, and the way that we're going to attack graphing this one out, yesterday I taught you about how you could try the intercepts. Today we're going to use a table of just some random values. Okay, now I always find plugging in x equals 0 to be a good starting point. That's an easy point to plug in. And who can tell me, somebody tell me what special point is it where x equals 0? What do you think? What special point is it? Go ahead, Luke.
Origin.
All right, so sometimes this can be at the origin. The origin is where x equals 0 and y equals 0. But perhaps it won't always be at the origin. What happens if I don't move to the left and I don't move to the right, but perhaps if I move up? Like in this case, I would move up 2 because negative 1/3 times 0 plus 2 equals 2. That would be my first point on the line right there. What do we call a point on the y-axis? And I'm purposefully not calling on Jake since he just answered one. Paul? Not range. Oh, come on. We talked about a police vehicle yesterday.
Oh, intercept.
The what intercept?
Y-intercept.
The y-intercept. Very good. Okay. So the y-intercept is a good point to start at. I get that by plugging in x equals 0. Okay. Now let's try plugging in some other points. Let's plug in x equals. Okay, so we got negative 1/3 times 1 plus 2. And that's going to be 5/3. So 5/3, when x is 1, 5/3 is, oh, not 5/3, pardon me. Or is it 5/3? Let's see here. 2 minus 1/3 is 1 2/3. Yeah. Okay, perfect. 5/3. So I'd probably be right about there. And I can plug in 2. We got negative 1/3 times 2 plus 2. Quentin, turn your cell phone off, please. Or Alex, or whoever that was. Let's see here. What's that going to be? 4/3? Y'all double check my arithmetic for me, please. But there we go. There's a third point. Now you might say, well, Coach Morgan, I remember yesterday you told me that 3 points constitutes a line and you're good to go. In your class, you like 3 points. But what is it about these 3 points that I picked that is maybe a little bit not so satisfying? Okay, so they're close to one another. That's a good point. If you put 3 points that are close to one another, then your line still might be off kilter just a little bit. What else about them? Anything that strikes you? Go ahead, Lewis.
Oh, there's only one that touches an axis, like an intercept.
All right, so there's only one that touches an axis or an intercept. So in other words, we didn't find the x-intercept. That's true. And then also, these two are non-integers. And I really do like to plot integer points, right? Points that are on the tick marks, you know what I'm saying? So like, if you continue on this pattern, if we go on to x equals 3, negative 1/3 times 3 plus 2, we wind up getting another integer value. So in other words, if we were on graph paper, that point would be right there. Now, can you pick up on the pattern here? Do I need to do x equals 4 and x equals 5, or what might be a smarter value to pick? What do you think, Charlie? Yeah, very good. X equals 6. Because 6 times negative 1/3 would be negative 2, plus 2 would be 0. Let's see, 1, 2, 3, 4, 5. I need to extend my x-axis just a little bit. And there's 6. Okay, and that makes good sense. By the way, that's also the x-intercept. Okay, so what we're noting is that we like these points where we get an integer result. And you can be smart about it like Charlie was and kind of pick up on the pattern. Okay, James, describe for me the pattern. What's happening in each of these times with the x and comparing that with the y? What's going on? What are we doing to get from 0 to 3 to 6? Adding 3. So my next smart point would have an x coordinate of 9. Excellent. Okay. And then can you also describe for us what's happening to the y's? What are they doing? From 2, 1, 0, what would my next? -1. Good. So we can recognize a pattern, fellas. And we can say, oh, yeah, okay. And you know, of course, if I wanted to extend my line over here, I wouldn't have to, but look, 1, 2, 3 more, and then we've got our next integral point right there. What do you notice about, Mossy, what do you notice about all of those points that we just found? We just found 6 whole points. They are all on the same line. Can I give you guys a vocabulary word today? All right, that word is collinear, Tiago. That word is collinear. What do you think collinear means? All right, so not numbers that work together. That's not a bad guess because like my co-workers, we work together. Co as a prefix means that they have something together in common. What do all those points have in common again? They are all on the same line. So collinear, right, means that they are all on the same line. And I know my line's probably not straight because of my non-equidistant tick marks. But hey, what are we trying to do here? We're trying to describe the pattern that James was just telling us about with the x values and the y values, okay? So every time my x goes up by 3, my y goes down by 1. So visually, what we're saying is that every time we go down 1, we can go to the right 3. Every time 1, we could go to the right 3. Every time we go down 1, we could go to the right 3. What is that pattern referred to in Algebra 1? Slope. All right, good. Joey, is that what you were going to say?
Yes.
Okay, good deal. Slope is the relationship between, what are our 2 R words that we probably have heard before? Slope is rise over run. If you haven't heard that before, you can jot that down. So we're going to talk about slope a lot this year, right? But I just used 2 R words, rise over run. We'll talk about that later on, but I just wanted to sprinkle that in as sort of a look at coming attractions, okay? This winter, in room 101, there will be 2 R words of importance. One is rise. The other is run. Ah! Slope, coming to you, November of 2020. All right, you guys try one. All right, so we're going to graph this line now. We're going to use a table of values. So in other words, you are free to pick whatever x values you want. And BT dubs, I didn't tell you this, but x values are usually the ones that we pick. Those are our, quote, input variables. And then we get out the corresponding y values. So x is our input, y is our output. So Quentin might pick, 3 or 4 different x values and plug and chug and get the matching y values. And then Mossy might pick completely different x values and y values. And they would be graphing the same line. Okay, because how many points did we say were on aligned yesterday? Infinitely many. While my son family have been on this beach trip. Apparently, he has learned to play ping pong. They had a ping pong table at the condo, so he and his buddies have been ping ponging it up all week. I might have to find a way to get a ping pong table at the house now. You guys ever have a ping pong table at your house? Long time ago. We got one in the baseball locker room. You guys seen the baseball locker room? You guys done tours yet? Or y'all do that in the 8th grade, don't you?
We were supposed to go on our tour this year, but it got canceled.
Gotcha.
Christian Brothers is coming to visit us today.
No kidding. Nice. Well, we had some kids up here yesterday that were touring around. So maybe you guys will get to do some tours here before too long. Anywho, we got a ping pong table in the baseball locker room. And so it's a well-known fact around campus that the best ping pong players are the baseball players, because every day before and after practice, they get after it. I mean, they're just killing it. Well, in normal circumstances, not during Coach Kelso has hidden the ping pong paraphernalia.
Morgan, do you just want us to go until we get an X intercept and a Y intercept?
No, I just want 3 points. Remember how I said I just like 3 points? Now, I would like them to be smart points, like, kind of integer values. So, for example, if I plugged in x equals 3, that's not going to give me an integer as a result. It's not the end of the world. It's still a point on the line, just like all 6 of those in the previous example. But no, you don't have to get intercepts. What you do have to get is 3 good points. All right, I'm just going to call on 3 random people here to give me said points. All right, so Quentin, I mentioned you a minute ago. Can you give me one of your points? You're kidding me. You just said the number 7. What was your corresponding y value? What happens when I plug in 7 times a half? That's 7 halves. Minus 1, that's 5 halves. So your point, Quentin, would be 7, 5 halves. Is that what you're telling me? Okay. You marched the beat of your own drum. Kudos. Alex, give me one of your points, please. And I would like integers. Pick an x value. Pick a number. Psst, don't pick 7. 2 is a fabulous number. All right, so let's plug in 2 in our head. What we're doing is we're plugging in, Alex just told us 2. We're going to plug that value in for x. Now, what's 2 times a half? Minus 1, 0. So, Alex, when I plug in x equals 2, I get a corresponding value of 0. Now, Quentin, how come Alex's point, how come I like his point better than yours? Very good. So he's got integers as a result. In other words, remember what integers are? Those are positive or negative counting numbers, or 0. And we've got our tick marks. In other words, so 2, 0 is much easier for me to plot than 7, 5 halves. Now, the reason I was giving you grief about 7 is I don't even have to have 7 tick marks on my x-axis. And I'm like, you can make me make more tick marks. That would be like, well, why didn't I pick, 28? Why didn't I plug in x equals 28? Okay. What would have happened, Jake, if I had plugged in x equals 28? What would my corresponding y value be? What's 28 times a half minus 1? 13. So I wouldn't want a dadgum come over here and have, like, it'd probably be like way up here somewhere and have the point 28, 13. I ain't going to graph that out. That's not a smart point. Yeah, I mean, shucks, you could have plugged in 100. And you would have got, what, 49. You're going to want to come all the way over here and get 100, 49? I don't think so. Okay, so when we pick, and of course, I hope y'all know I'm just kind of being silly here with you, but when we pick x values to try and plug in, for Pete's sake, they might all, these might all be collinear. In fact, they are all collinear. But they're not, easily graphable points. We want easily graphable points, okay? Drew, can you pick me another x value that would be good to plug in? I'm not happy with 1. 1 times a half is a half. A half minus 1 is negative 1/2. Non-integers. Now, could I graph out 1 and a negative 1/2? Sure, I could. Look, there he is, right there. Oh, that's such a cute little point. Actually, the computer didn't even like that one. There you go. Okay, Drew, pick another point. Pick a smarter value. 6. Now, why is 6 better than 1 and 7? Because when I plug it in, I know I'm going to have to multiply it by what? By 1/2. And so an even number would be a, quote, smart number to plug in here. Just like in the last example, I didn't say this, but what did all your smart values have in common in the last example? They were all multiples of 3. Okay? So being wise about what you plug in, okay, can try to help you guys out. I want to make your life a little bit what? Easier. Work smarter, not harder. All right, so Drew, what was that second one that you told me again? 6. All right, I like, even though I don't have 6 tick marks, I like 6, because 6 times 1/2 is 3. 3 minus 1 is 2. 6 comma 2 is a pretty good value. We'll put it right there. Okay. Now, let's see here. Who told me 2 comma 0? Was that Alex? All right. What's special, about Alex's point? Jake? That's the x-intercept. Remember, the x-intercept has y as has 0 as a y coordinate. So, Charlie, what would the y-intercept have? Very good. 0 as an x coordinate. And didn't I dadgum say in the previous example, fellas, that I think 0 is a fabulous point to start with when you're plugging and chugging? Thank you, James. Thank you. I was fixing to say, ain't nobody trying to plug in x equals 0? Because what you can do with plugging in x equals 0 is you can just do the cover-up principle. Y'all heard me talk about the cover-up principle before, right? We mentioned it yesterday in class. If I'm plugging in x equals 0, I might as well just cover up that term with my hand. And I would read what the equation says now. Y equals -1. And I've got very little thinking to have to do. So 0, -1, that is my y-intercept, okay? And by the way, we got our 3 points now. That line out, okay? Now you're going to learn many techniques about linear equations this year. One of them is graphing them using a table of values, okay? Now, when I describe something, an equation, I call it a linear equation. That tells you that the shape is going to be a line. That's the word, linear, L-I-N-E, and then A-R at the end. So linear means that the graph is going to be a line. However, you're not going to just study linear graphs this year. You're going to study other graphs. I mentioned yesterday you're going to study quadratic functions. Their graph is a parabola, okay, kind of like a horseshoe shape or the St. Louis Arch, that kind of shape. That's what a parabola looks like. But you're going to study other shapes as well, okay? So check this out. You're about to do some algebra 2. You ready to do some algebra 2? Now this is a nonlinear, non-quadratic equation. This is just some funky equation that I've just cooked up. Are you going to write it down? Write it down. And guess what you're about to do? You're about to graph it out. How do you think you might go about graphing this out? What technique have we been practicing today? Plugging in numbers, making a table of values, making an input-output table. So here's, I'm gonna type something up here. This is of the utmost importance. I want you to write it down in your notes, okay? Whenever you are asked to graph a new function, function is just, in this case right now, just a word we're using to describe a relationship between x and y, okay? So whenever you're asked to graph a new function, consider making a table of values first. Gather ordered pairs. And I'll say enough ordered pairs. Gather enough ordered pairs such that the whole shape is discovered. What I mean by whole shape is that, I mean, a line is a line. We know what a line diagram looks like. But like, if I have, this curve doesn't do it, but like if I had just a few points like right here, here, and here, I'll zoom in case y'all can't see that from the back. Then I might be tempted to think, oh yeah, that's what this shape looks like. It's just a hump like that. But then, if I don't pick some points over here, if I don't pick enough points and get enough ordered pairs, this might be a curve that does something like that, and I would have just forgotten to check the whole scheme of things. So in other words, like whenever you're asked to graph a new or like something that you haven't done before, make a table of values. That is so important. I have to literally yell at sophomores and juniors who are taking Algebra 2 and pre-calculus when I give them a function, say, hey, we're going to graph this rational function out today, okay? Or, hey, we're going to graph this logarithmic function out today. And they're like, duh, I don't know how to graph that. I've never practiced that before. And I want to just shake them and be like, bro, you have made a table of values before. Try that. Okay, now, here's my question for you guys. What the dump is going on out here? Having a freaking cornhole party out there. Coach Cannon, he's so fun. Apparently, if the boys win a game of cornhole today, they get to go first in line at lunch. Isn't that nice? I have to get out there and show them my skills. I'm not as good at cornhole as I am at horseshoes. You guys ever played horseshoes before? Well, I'll take you down, son. I'll take you down. Me and Teddy played horseshoes a lot this summer. And I would let him, if you haven't played horseshoes before, here's how this works. You got one stake in the ground over here. You got another stake in the ground over here. Usually you have like a little box pit kind of thing with sand all in there. And what you're supposed to do, is you're supposed to stand right here. And you're supposed to throw the horseshoe down this way. And a ringer is when it goes around the thing. You get 5 points for a ringer. A leaner is when it's leaning up next to the post. You get 3 points for that. And then if you're within one horseshoe's length, you get 1 point. That's the scoring system. And so we played a 21. But I let Teddy, just because he's a little bit smaller than I am and weaker and not as seasoned, I let him stand right here halfway and throw. And so he beats me every time. And it makes me so mad.
Saying almost only counts in grenades and horseshoes.
Absolutely. Hand grenades and horseshoes. Because if you get almost a ringer, you get 1 point at least. All right. Anyway, Coach Cannon's out there playing some cornhole today. We'll keep our eyes open. All right. What I wanted to ask you guys, okay, is can you please let's think of 5 good inputs for this kooky, made up, fake, function here that I'm asking you guys to deal with. This is not an Algebra 1 question, but the premise is what we just got through talking about. So somebody put your hand in the air if you think you're a player. Tell me one good number to plug in, and I promise I won't yell at you. Charlie, 0 is a fabulous number to plug in. Drew, 2 is not a fabulous number to plug in. Jake, I don't know what the square root of 2 is. Well, I do. It's 1.41 thereabouts, but I don't know an integer value. Paul? 4 is a fabulous number to plug in. Tiago? 10 is not a good number to plug in. Again, I don't know what the square root of 10 is. Jake? 9 is a fabulous number. Y'all skipped 1. Literally. Get what I'm saying, Alex? I said y'all skipped 1.
Ooh, 1.
There we go. 1 is the number. Okay, why are these, Quentin, why are these good numbers to plug in? Yeah, absolutely. Because when I plug in an x value into this function, right, look what I'm going to have to do. 0 squared minus the square root of 0 plus 1. 1 squared minus the square root of 1 plus 1. 4 squared minus the square root of 4 plus 1. 9 squared minus the square root of 9 plus 1. So you get the idea? So plugging in some smart values is appropriate. Now, technically, could we have plugged in 2? Absolutely. If I had plugged in 2, I'd have 2 squared minus the square root of 2 plus 1. If I'd plugged in, what'd you say, Jake, 10? If I'd plugged in 10, right, that'd be 10 squared minus the square root of 10 plus 1. And I would get a number. I'd get a legit, mathematical number. It would just be a non-integer, okay? So like, what's 2 squared? 2 squared is 4 plus 1 is 5. So this would be 5 minus radical 2. Over here, 10 squared is 100 plus 1. So this would be 101 minus square root of 10. Like, those are legit numbers, right? Somebody tell me, what can I not plug in? What could I not plug in, Paul?
7.
What the hell, I could plug in a 7. All right, just like I plug in a 10 or 2. So 7 squared minus square root of 7. I don't know what square root of 7 is, but I could just leave, what's 49 plus 1? 50. We'd have 50 minus square root of 7. So that's okay. That's a number. That's legit. Charlie? A negative number. Now, this might be putting the cart before the horse here, but why can't I plug in a negative number? Jake? So in other words, square root of a negative at this point in your math careers, not doable. Okay, can't take the square root of a negative number in algebra 1. And so, like, now we're getting into the realm of, oh, you mean I can't always, with every function, just plug in whatever I want? If I wanted to plug in 42 billion, or if I wanted to plug in negative 17.3, if I wanted to plug in pi, if I wanted to plug in negative square root of 2, I can't just plug in whatever I want? And the answer is no, you can't. Sometimes there are restrictions to what you can plug in and what you can't. Tiago.
How would you figure out the square?
I'll teach you that if I have you in algebra 2. It has to do with the imaginary number I. Y'all ever heard of imaginary numbers? Yeah. Okay. Well, the long and short of it here, fellas, is that there are sometimes restrictions to what you are allowed to plug in and what you can possibly get out. And Paul, I think, mentioned the word range a minute ago. Range refers to the set of numbers that you could possibly get out for a particular function. Do we know what the set of inputs, what we're allowed to plug in? Do we know what word we use to refer to that? The domain. Excellent. You'll hear me teach you later on, probably next week or the week after, about domain and range. Okay. But domain is the set of numbers you're allowed to plug in. Range is the set of numbers that you're allowed to get out. But again, I don't want to get off kilter here. Let's get back, and this will be our last slide for today. Let's get back to linear functions, to some nice, comfortable arrangements. And here, actually, we are going to talk about slope today. I thought we maybe wouldn't get to it, but here we go. I'm going to pretty much translate for you, since we only have 2 minutes in class, what I would recommend putting in your notes. Number 1, write down what's in red up there. That's your second form. The first form was standard ax plus by equals c. Second form is called slope-intercept, y equals mx plus b. And you've actually seen that in action a couple times today already. You might not realize it, but I gave you a couple of y equals forms already. Now, m is the slope and b is the y-intercept. That's important for you to note. M is the slope. All right. B is the y-intercept. Now, we've talked more about the y-intercept than we have about the slope, so let's discuss slope. Slope is rise over run, okay? My visual representation usually is I use this rolly chair, and I sit down in it, and I say, all right, I know you can't see me at home very well. Here, I'll do that. There we go. So I'm sitting in this chair, sitting in my office with a plate of grilled bacon. Call my man Dwight just to see what was shaking. Yo, Dwight, this town is dope and pretty. So check out how we live. In the Electric City. All right, anyway, sitting in my chair here. And if I wanted to go over to that pencil sharpener, assume this chair doesn't roll, what do I have to do first? I gotta rise! And then I gotta run. Okay, so slope is the comparison. I see, what little Greek letter is that? Triangle. Do y'all know what Greek letter that triangle is? Delta. Delta stands for come on in. It stands for change. Okay, delta stands for change. What's up?
It does. I have a math question. But
Oh, fun.
If you're recording, I'll come and ask you
later.
You can come and ask me in 30 seconds. I'm gonna kick these yahoos out of here.
I'll just stay here.
Awesome. All right, so when we talk about rise over run, okay, that's change in y over change in x. And about rise, that's a vertical change. I'm getting up out of my chair and I'm running over there. All right, so since I'm out of time today, here's what I want you to make sure you have written down. Slope-intercept form. Okay, have written down that m stands for our slope, which is rise over run, and b stands for the y-intercept that we've already talked about. And then tomorrow we'll practice some more stuff. I say in purple right here that we're not going to go in great details about slope until the next section, but this is just a little peek at what it is. Y'all got any questions before I got to send you out of here? All right, fellas, fabulous job. Thank you for logging in today. Joey, you win the Diligence Award for being online, even though y'all don't have school today. Live Jesus in our hearts. Excellent. Thank you, fellas. And I challenge you to go play cornhole on your way out before you leave. See if you can make one. Talk some smack